I'm Jona, I'm a machine learning project lead at dida, and today I will talk about information extraction from free-form text using BERT. And I'll do that along a project we did with one of our clients, Idealo, some of who are actually here today, which is cool. And although this is obviously going along with this project, I guess most of what I tell you today is applicable to a broader range of problems. And so the project we did together was actually a proof of concept project, so not everything is tried, what I will explain in the next half an hour, but you'll see that we nevertheless reached quite nice results. So without further ado, my agenda for today, I will give a general introduction into the abstract problem we're trying to solve, and then explain why this problem is relevant for idealo and how exactly this looked like in their setting. I will talk about the preparational steps we had to take in order to actually start with the machine learning, and then obviously we'll talk a bit about the machine learning models we used. We used mainly two different variants here, and then I'll come to a conclusion here. So, general problem setting. I want to find information in free-form text. So, for example, take this text here. This is a description of the building we're in here today. So, apparently it's a temporary timber construction in Gleisdreieck Park, obviously. And I want to extract some information out of it. For example, what kind of building material is this? So my desired outcome here would be a text section of this input. So in this case, timber. This I want to try to solve. I probably can solve this task, or I definitely can solve this task with pre-trained methods already. Don't need to do any machine learning, but as soon as I have more complex texts and more complex knowledge needed to answer these questions, I actually need to train things. A few assumptions we make in this setting here. We have already machine-readable text. Otherwise, I would need to do some kind of optical character recognition, for example, first. But here we assume we just have machine-readable text. And also, I assume that the text has no structure or layout. It's really just free-floating text. All right, so this is a general problem setting. And why is this question relevant for idealo? So some of you might know idealo. It's a price comparison platform where I can see prices for a single product from different merchants, but I can also search for a group of products and then filter down by different properties of these products. For example, I don't know, an iPhone, and I want only the iPhone with a certain amount of storage. So what idealo does in order to facilitate this, it brings together catalogs of different merchants, actually over 50,000, and puts them into a unified and consistent catalog and tag system in order to make it searchable for users. And the way they do this is that sometimes they get structured information, but sometimes they also get unstructured information in the form of just free-form text product descriptions. And out of these free-form text product descriptions, I want to get structured information in the form of product attributes. For example, the storage an iPhone has, or the weight a certain product has, things like that. To make this a bit more tangible, let's look at an example. For example, I'm looking for terrace roofs. Maybe, because, well, some people do have terraces, even in Berlin. And one thing I need to mention at this point is you see the pages in German here, and all the examples I will show are in German, because the whole project was carried out in German as one of the most important languages where idealo is operating in. Right, so I want to look for terraces, and you see, okay, maybe I want to filter for a certain width and height because, well, my terrace is a certain size. And then the descriptions which arrive at idealo from different merchants come in very different formats. So I could have one where I have width, height, and depth designated separately. I could have them all in one string, separated by axis. I could only have two of those and a third one missing. I can have them in centimeters or in meters. And so you see, this is all pretty different, and I need to parse all this different information and unify it in order to make it searchable. So before we talk about how we try to solve this, let's quickly talk about how this is currently solved in idealo, because this motivates why we might need a machine learning solution here. So the way this currently works is a dictionary-based approach, meaning that basically there's a huge dictionary where all the possible values for a certain attribute I want to extract are manually entered and then stored, and therefore I can then find these values via string matching in my incoming offer texts. Right? So I could, for example, so I actually have more than 5,000 different attributes, which I'm interested in theory. Not all of these attributes apply for every single product. There are subcategories for products, and depending on the subcategory, I know that only a certain amount of attributes is relevant, right? For, I don't know, maybe I'm not too interested in the weight of my terrace roof, for example, but only in the dimensions. So I know this in advance. And then they might be augmented with some kind of synonyms or translations, and I will also, and I can also define relevant categories. So I can exclude certain attributes I do not want to look for a certain product. But nevertheless, this amounts to quite a lot of manual work. So for example, for the attribute brand, so Hersteller in German, I actually have 81,000 or over 81,000 different possible values in this database. So you can imagine it's quite some work to actually maintain this. So let's talk more about the advantages and disadvantages of this current approach. Well, one of the obvious advantages is it's human understandable and tunable, because I just type in a value and I can be more or less sure that this value will be found in an incoming offer text, right? No matter what else happens. I can also tune it to a high degree of accuracy, because I know if I type in a value, then only this value will be found. And it makes up for a nice collaboration between machine and human, because I can tune the machine by entering new values, and it will execute exactly this. The downside, well, pretty obvious. It takes a lot of effort to maintain this. I think, if I'm not mistaken, roughly 100 people at idealo are actually employed for doing just maintenance of this database. I need to add every new value explicitly. If this value hasn't been in the database before, I cannot find it. And I cannot use any regularities I get in my text. So for example, for the width example, or the dimension example, I cannot discover, okay, whenever there's width, and then a value that this is probably the width. And I cannot, more generally, I cannot take context into account. These downsides are particularly severe for numeric values. You can imagine if I need to enter every numeric value, so for example, every weight a certain product can take on in order to find it, this is a lot more work than if I need to enter every color a certain product can have, because my search space there is somewhat more limited. So this is why we, in this proof of concept, actually focused on numeric values, because they are the most painful to maintain. And we also restricted all the products we're looking at a certain overcategory called the DIY products, just to make this tractable within a reasonable amount of time. All right, so now we know why it could make sense to actually employ a machine learning solution here. And we can talk about the preparational steps we need to take in order to actually be able to do machine learning. So the first one is pretty obvious, and probably needs to be done for actually every machine learning project. I need to define a performance metric, just so that I can be sure I know how well my model performs. Then the next one is very specific to the problem we have here. I need to find candidates for numeric product attributes. This is actually a nice thing about this problem, because I know I'm only looking for numbers. I can restrict the potential text sections I want to give out as a result to only the numbers, because I know I'm looking for numbers, so I don't need to output any free-form other text. And we actually can do this in a rule-based manner, implemented by a custom parser for us. So we find all different number formats. May they be combined, different values for dimensions, different comma notations, and everything. And then next step, again, pretty general for a machine learning project. I need to manually label some candidates into training, validation, and tests, so I can actually properly train something. And what we then did is actually also automatically label a lot more candidates, because we just had limited time and it's a lot of work to do this manual labeling. We thought it might make sense to come up with something which actually helps us to create an even larger data set, even though it might not be as nice quality as the manual labels. All right, so let's quickly talk about these different steps. Performance metrics are pretty easy. Since this is basically a classification problem for every single number, I want to know, does this correspond to a certain attribute, and if yes, to which attribute? So I can just use classification metrics, meaning precision, how many of the predicted attributes were actually correct, recall how many of the correct attributes were actually found, and then the summary score of the two with the F1 score. All right, let's talk about labeling. We actually had manual labelers helping us there. And what you see here is a screenshot of the actual labeling interface we used for this. And on the right, you see an example of an offer text coming into idealo, actually only a section because we cut it at some point. And on the right, you see what is already in idealo's product catalog for this product. And you can observe multiple things. So one is, there are more values on the right than there are on the left. So this is a common scenario. Not every merchant has all the information you might want to know about a product in their offer descriptions, so this happens. And then also, it can happen the other way around. There are more interesting values already labeled as a certain attribute, which actually are not present in the product catalog. This can also happen, and it's pretty natural, because, as I said, it's a lot of work to maintain all these product attributes, so you cannot focus on all of them if you need to do this manually. So naturally, even though there might be more information somewhere around, you don't have it in the product catalog because you need to prioritize when doing this manually. So in order to support our labelers, we actually implemented some kind of string matching solution which tries to find the values which you already know of in these texts, pre-label them, and then present them with these labels, so they only need to correct them and add the new ones which weren't already in the product catalog. And doing this, we were able to have roughly 6,000 labeled data points for 650 different classes. So the classes here are the different attributes, which isn't actually that much if you think about it, right? It's less than 10 samples on average per class. So we really do not have that much data to train here. And therefore, we thought, okay, maybe it makes sense to come up with more data without having to manually label them. And we actually used exactly this approach here we used to support our labelers to just create an automatically labeled data set with over 1 million data points. Although we know the quality of this data set will not be as good as the manual labels because there are discrepancies between what is in the product catalog and what we find in the product descriptions. All right, now we have everything we need to start with actual machine learning, and we can talk about that. The two different models we tried both followed the same workflow, actually, a very similar workflow. So we start with a product description, for example, here, something about a power socket. We do the candidate detection, rule-based, with a custom parser, just finding numbers. Then we send this to some kind of language model and calculate an encoding and get a prediction out of. So this encoding, what is this? It's just a vector representation of my single numbers. So I just get a vector out, and it somehow represents, hopefully, the meaning of the number I found. And one additional thing I mentioned earlier already is that we also input the product category. So in this case of the power socket, maybe something like electric appliances. I know this in advance because idealo has algorithms in place to determine this. And this just narrows down the attributes I'm interested in because, yeah, well, I'm maybe not interested in the weight of my power socket, but only in the voltage it's usable in. So that facilitates the problem a bit. All right, so the core piece of this whole pipeline is our language model, and let's talk a little bit about that. So in this case, we used BERT as a language model. And yeah, well, maybe some of you know this already. I will nevertheless take the time to quickly explain a little bit what it does and how it learns. Stands for bidirectional encoder representations from transformers, meaning, okay, we get some kind of context in both directions, and it's based on the famous transformer architecture, which is up to date, very, very relevant. The attention mechanism in the transformer architecture means I can actually look at context, which is, in the case of numbers, especially relevant. It builds on this transformer architecture, okay, and it's trained in an unsupervised manner on a huge amount of freely available text data, which means it has a lot of world knowledge already and baked into it, and I can use it later on. And what is quite relevant in a commercial setting, I get pre-trained versions of this in multiple languages, which are licensed in a way that I can actually use them commercially. We used BERT in this case, but BERT is not the only transformer-based encoder you can have. So maybe this little picture will show you all the dependencies of different transformer-based encoders you have, along with also not really encoders, but generative models like the famous GPT family, which probably everybody knows today. What I want to say with this slide is, okay, just because we use BERT, it doesn't mean we are tied to it. You could also use another transformer-based encoder architecture and still be fine with it. Let's look quickly at how BERT actually learns this context understanding and this world knowledge. And this is actually done in 2 different steps. I start with something to learn my general language understanding, also known as pre-training. The nice thing about this is general usable because it's general language understanding, and I don't need to carry it out for every specific application, which is again nice for us because we don't need to train it for a certain problem setting. We can just take the pre-trained version. Needs lots of compute resources and large amounts of data. Again, none of our problem because we can just get it. How does this work? It's actually happening in 2 steps again, and I'm learning linguistic context on 2 different scales. The first and probably most important step here is known as masked language modeling. And here I learn connections or context between words. The way this works is I just take a full sentence from any freely available text, mask out one word, and or multiple words, and then just put this through BERT and let BERT predict the missing word. And this way I learn in which context different words appear. Then the next scale on which I learn linguistic context is called next sentence prediction. And there I just put in 2 sentences, sentence A and B, and let BERT predict if B follows A or not. Actually, the second part has been shown to be way less relevant than the first part in order to get language understanding. And some newer versions or variants of BERT encoders actually don't use this second step anymore at all. All right. Now I have a network which has general language understanding, and I can actually specialize my network. For this, I need less data because it already knows quite a few things. I also need less computing resources, but I need to fine-tune it for my certain tasks. So I need to perform it again for every specific application, and this is where we come into place. And right, so now we know what this language model roughly does. How does this work in this specific setting? We tried 2 different variants here. One we called BertSeg for BERT segmentation. The other is BertQA for a question answering approach we choose here. And we start with the BertSeg approach. We start with a very general step, quite often necessary if you use transformer-based language models. We tokenize the text. And that means we just split it into words or subwords. And also one custom step we do here is we mask out every number we found with our candidate detection with this special number token. And this is in order to not overfit on certain values. If you think about the voltage example, I do not want to learn my network that whenever it sees a 220, it always assigns voltage to it. But I want to have the network deduce this from the context, actually. So next, I put this through my BERT encoder. It's my pre-trained architecture. And I actually get vectors out for every single token I put in. Then I'm only interested in the vector which corresponds to my number up here, because I want to find numbers and classify them. And the nice thing is that after it goes to the BERT encoder, this vector here doesn't only depend on the number up here, but it actually depends on all the tokens I put in. This is the context understanding BERT comes with. Right, so next I know which category my product comes from, because this is an input provided already. And therefore, I can just take this vector and classify whether this vector here would correspond to one of the potential attributes. I just put it through a classification layer, and this classification layer is specific to the category, because I do not want to have a classification layer which has 650 different classes. With the amount of data we have, very hard to train. I'd rather restrict it to maybe the 20 relevant attributes which are relevant for power sockets, for example. After this, I get out a classification. Ideally, I get out that this is the voltage, and I'm done. I can do a similar thing, but not quite, with a slightly different architecture we called BertQA. Again, we start with tokenizing our text and putting in the text into our BERT model, but this time we actually add the attribute we are looking for into the input. That means everything goes through the BERT encoder, and we get a vector out, but this time the vector, which is down here and corresponds to our number, does not only depend on the context of the offered text, but also depends on the attribute we are looking for. And this has the nice effect that now I don't need to have a category-specific classification layer. I don't even need to have a multi-class classification layer, but I can just have a single classification layer which just gives me a yes or no answer, answering my question whether this number corresponds to the inputted attribute up here. Therefore, it's we call it question answering architecture here. This has a downside, as some of you might notice, because I cannot find all my attributes all at once here, because I need to input the attribute into my BERT encoder, and therefore I need to do this whole thing as many times as attributes I'm interested in. So my inference time scales with the number of attributes. The upside of this is that I have better generalization capabilities, because I don't have separate classification layers for everything. I just have this single binary classification layer, which is the same for every single attribute, same for every category. And I also could, in theory, just input a new attribute the model has never seen in training before, and still probably get a reasonable answer to this, because I can leverage the pre-training of BERT and also the domain-specific knowledge BERT has learned through my training. For example, if I train for a lot of technical products and knows a lot of technical properties, I get a new technical product which has a slightly different property, I probably will be still able to predict something nice just with this, even though I have never seen this before. So let's quickly look at a few examples of the output of this BertQA model. Okay, again, we have here a title and a description of some kind of technical appliance. I think it's a timer for your power socket again. I do my candidate detection step, find different numbers in my text, and then I need to classify them. And you see, okay, this time I've recognized everything correctly. I do not miss a number which we're interested in. And also, you see that there are a lot of numbers in yellow in here which I ignored correctly, which is also a relevant thing. I don't want to list numbers which don't play a role in my product catalog as well. Another example does not always work. Again, I find all the numbers, rule-based, then I recognize two things correctly, but I miss one, actually, this time. Well, happens. And then I also ignore something correctly, which is especially nice because, I mean, it's basically the same number as the power consumption here, but it's still correctly ignored because it is not the power consumption at this point. All right, so some nice examples how this work. Let's look at actual quantitative performance. Right, a lot of numbers, but the one important thing here is that this is the best model we get. We have a precision of 0.82 and a recall of 0.62, and this was with our BertQA architecture using our manual labels, the 6,000 from the beginning, and the 1 million weak labels we use. Now you might say, okay, well, 0.62 in recall isn't that high, actually, so why are you proud of this? Maybe look at the numbers here to the right. So the numbers here to the right are not an actual machine learning model, but these are the scores that we get when we use our matching procedure we use to create the automatic labels, and compare this with what our manual labelers did. And that shows, okay, the recall of 0.5 just means our labels just found a lot more values in these texts than we have in the product catalog. So having a recall of 0.62 is already 12 percentage points better than what the product catalog roughly can do today. So it actually is quite a nice improvement. And I mean, this is pretty to be expected that this value is so low because, as I said in the beginning, you cannot care for all the attributes you could theoretically be interested in for a product just to keep the work doable by people, right? So actually we have quite a nice improvement, especially in recall, meaning we have more information in a structured way available to customers. One other thing I would like to point your attention to is that this column here, if you look at BertQA, and this is only using the weak labels, we didn't actually use any of the manual labels, and we already have a matching performance in recall compared to the manually curated product catalog, which is also pretty nice. Okay, let's compare them a bit. So we have BertSeg, which is fast in inference compared to the BertQA approach, whereas in the BertQA, the inference time depends on the number of potential attributes. BertSeg cannot predict possibly any unseen attributes, whereas BertQA has this nice generalization capability. And in BertSeg, you have like knowledge sharing only between categories in the BERT encoder itself, because they have these category-specific classification layers, whereas in BertQA, I have complete knowledge sharing, basically, because I use exactly the same classification layer and exactly the same encoder for every category. And well, last but probably most important, BertQA has, as we have just seen, the higher extraction performance. So lastly, let's maybe talk about the elephant in the room here. Some of you might have thought, why not just use ChatGPT for this? Can't it just do this? I mean, is it so hard? And the thing is, I would say, well, in some easy use cases, yes, just use ChatGPT for this. But as soon as I have domain-specific language and very intricate differences, for example, between technical product properties, ChatGPT will come to an end. And therefore, I can use the ability to actually fine-tune my model to exactly the domain I'm working in and specialize it. So that's nice. Then another very important part here is privacy and data protection. With the models we developed here, I can just host the model myself and have full control over my data flow. It doesn't need to leave my premises if I don't want to. And also speed is a point here. The model here, BERT, is way smaller than what is behind ChatGPT, so I have fast inference time and my models are less resource intensive here. And the last one, a bit of a follow-up from the first one, is sustainability. Because my models are way smaller while still giving a good performance, I need way less energy to actually run them, and that means I'm just more sustainable in the compute I do. So let's conclude. We've seen that I can train models which outperform these manually expert-tuned systems after a short period of time, especially for these numeric values. And I've seen that creating weakly labeled data from existing databases can help a lot, as we've seen in the metrics for the BertQA trained only on the weak labels. And this actually has the potential to improve idealo's tag or product attribute inventory, because we've seen this difference in recall between the existing product catalog and the BertQA model. And as a side note, we can actually use a similar approach for text attributes. We also did a POC with this, which also gave nice results. But in order to keep today's talk short, I limited myself to this. And as a little outlook, so right now I only talked about unstructured free-form text. But what if my text is actually structured and the location of my words play into account when I want to determine the semantics? Well, then I can refer to a talk by my colleague Augustus Stoffel this afternoon about graph neural networks versus transformers for information extraction. And if you're wondering what other nice and interesting things I can do with language models, I can refer to the talk by Jakob this afternoon as well about domain-specific semantic search. Thank you very much for your attention.
Yeah, thank you very much, Jona. We have a little bit of time, so the question microphone is here in the front and in the back. So if there are any questions from your side.
Thank you for the very interesting talk. My question is, you had an example where an attribute was wrongly detected. How easy is it for your model to correct this compared to the manual data set? Because in the manual data set, you just correct the entry and then you're fine. How much or how time consuming or is it to correct it with your model?
Well, it's hard to say, and I guess that's one of the main advantages of the current system that, well, you have a high precision, right? Because you find things correctly. Although, when looking at the metrics we've seen before, also the current model can do mistakes, right? If I have a certain value input, like I have it knows the weight of certain product can be 220 grams, and then I find 220 in a different setting there, it might label it wrongly. So it's hard to say what the difference in correction here is. I would say one needs to take into account here that this is a POC project, and you have seen we had like less than 10 examples for every single attribute in the training. So this is pretty low for a machine learning project. So I would say with a bit more training data, good training data, this should increase pretty quickly, but it remains a statistical method in the end, right? It can still make mistakes even though maybe the error margin goes down.
Thank you.
So thank you for your talk. I was wondering, what do you think is most crucial for you to improve the model's performance? Is it really just more data, or do you need to fine-tune how you infer on the model, or what are the next steps?
I guess, well, yeah, more and good data is just always key here. And I mean, the nice thing here is that if you actually roll this out across a whole product catalog using especially the BertQA model, you could expect that it learns from categories it has already seen, meaning that I don't necessarily need more data for a category I already have data for, but maybe adding data from different categories where the semantics are somehow similar will also improve this. But I would say this is the main thing. I mean, there are a few more tiny tweaks you can think of. For example, this number token masking we do it to prevent overfitting, but maybe it could make sense to not just encode this being a number in there, but maybe encode an order of magnitude there, because maybe you know, okay, certain voltages will never go above 2000 volt or something like that, and then you can somehow encode that information in there. But apart from that, I guess the main thing is just good data and more data.
And maybe one follow-up question: how did you use the weak and the good label data? Did you only fine-tune on the good data and pre-train on the weak label, or how was your workflow there?
Yeah, so the standard setting was we trained first on the weak labeled data and then used the manually labeled data to even fine-tune further. But if you look at this one slide up, a bit more back here, we also did runs where we really only trained on the weak labeled data and only trained on the manually labeled data to see where we can actually get with that.
Okay, thank you.
Yeah, if there is one more question.
So what's your assumption if you would label a whole product category, from fine-tuning the model to labeling all the data that you have? What do you expect? How much time do you need for that? Can you make an assumption? Roughly?
You mean to implement it or
Yeah.
to train it?
Implement, train, and have all the data labeled.
Well, that's hard to guess because it really depends on. I mean, this was actually pretty hard for labelers to do, to the labeling, for example, because these are very technical categories,
Sure.
very intricate difference between attributes. Depending on how hard that task is, the labeling takes very different amounts of time, depending on how hard the problem itself is. Like, so for a good first proxy is always, if I, as a human, look at this text and it's immediately obvious to me which is the right answer, then it's probably also easier for the model to learn than if I need to think a lot about this before I get to the right answer. So a lot of variables here.
How much time did Idealo give you?
Yeah, exactly. That was my next sentence. I think this project ran for, I think, 3 months in the beginning. Yeah, and that was how long it took us to get there.
Okay, cool. Thank you.
Okay, I think I saw some questions, but unfortunately we don't have any more time to start punctually with the next one. But Jona will be around the whole day, so go to him, ask him about more details, chat him up. So then, thank you very much, Jona. Another round of applause.